Hello, good morning everyone. So let us start with our physics course. I'm going to teach you physics paper 2 of semester 5, quantum mechanics, nanomaterials and nanotechnology. So in the first part, let us start the quantum mechanics. In this part, we will see the failures of classical theory before start of quantum mechanics. We will see the failures of black body radiation, and then we start with the quantum mechanics. So in the first unit, this is the syllabus: failures of pillar of classical physics to explain black body spectra, Planck's radiation law, Compton effect, wave duality, de Broglie's hypothesis, concept of wave and group velocity, experimental demonstration of matter waves, Davision and Germer experiment, and last part of the first unit is Heisenberg's uncertainty principle, and I will discuss the thought experiment also. So this is the first part of quantum mechanics. So our first topic of discussion is failure of classical physics to explain the black body spectra. So the reference books are these for the entire paper. So let us list out the reference and textbooks. First book is Quantum Mechanics, Statistical Mechanics, and SSP, Solid State Physics, by D. Chattopadhyay and P.C. Rakshit. Fundamentals of Quantum Mechanics by P.R. Wagmare. Quantum Mechanics by John and Powell. Powell and Crispin, we can say. Quantum Mechanics by Matthews and Venkatesan. Quantum Mechanics by Ghatak and Loknathan. Quantum Mechanics by HP Singh, Bagre, and Kamal Singh. Quantum Mechanics by Atwal Anand. Advanced Quantum Mechanics by Satya Prakash. Introduction to Nanotechnology by C.P. Owens. Nanotechnology by T.J. Damling. Nanostructure and Nanomaterials by M. Balakrishna Rao, A. Krishna Reddy. Nanotechnology by Rakesh Rathi. So these are the reference books for the nanomaterial and nanotechnology. So let us start with the first part, that is black body, that is black body radiation. So we know that what is black body? It is the body which absorbs all the wavelengths, all the radiations falling upon it, and emits the radiation, and that is a function of temperature. The emissive power of black body radiation depends upon the temperature. So this is the black body. As I said, emitted radiation is a function of the temperature. So this black body radiation is nothing but thermal radiation, infrared radiation. So black body radiation can be shown like this. So along the y-axis, it is the energy emitted per unit area, that is energy density, and on the x-axis it is wavelength. So this is the curve of black body radiation. So at different temperature these curves are arranged. This is 5500 Kelvin, 5000 Kelvin, 4500 Kelvin, and 4000 Kelvin, and 3500 Kelvin. So as we know, the curve shows the energy emitted from the black body at a particular temperature. So at each temperature there is a energy radiation, and at particular wavelength at a given temperature, at this particular wavelength, say lambda m, the emission is maximum, the rate of emission is maximum. So this wavelength is called the lambda m. So this is the characteristic of that black body radiation at a particular temperature, and this temperature where the radiation is maximum is different for the different temperature. For this curve it is here, for this curve it is here, and for this curve it is here. It means it is shifting, lambda m is shifting towards the lower wavelength side as the temperature increases. So this is the important characteristic of blackbody radiation. The second type of characteristic is the area of the curve represents the total energy emitted by the black body. So if you calculate the area of this entire curve, that gives the total energy. More importantly, as the wavelength increases, as we increase the wavelength range, the energy radiation first increases like this, it becomes maximum, and at particular wavelength, after that particular wavelength, we have denoted that by lambda m, and it further decreases. So these are the black body radiation curves. Now, this nature of these black body radiation curves, few scientists try to explain this nature of black body radiation curve. They perform certain experiments and draw some results and give some theory. So, first theory given by the Stephens-Boltzmann law, that is in 1879. What he says, the energy emitted is directly proportional to the fourth power of the temperature, absolute temperature. E is equal to sigma into T to the power 4, where sigma is called the Stephens constant. So, or say power radiated, power means energy radiated per unit time. Power radiated is equal to sigma into T to the power 4. So here some modification, after some modification, power radiated is equal to sigma into Q to the power 4 minus T0 to the power 4. T0 to the power is, we can say, it is the ambient temperature, that is surrounding temperature. So this is the modification, where P is the total amount of radiation emitted by an object per square meter per unit time, we can say, as it is power. Sigma is a constant called Stephens-Boltzmann constant. It is given by 5.67 into 10 to the power minus 8 watt per meter square per degree Kelvin. Sorry, per fourth power of degree Kelvin. T is the absolute temperature of the object or black body, and T0 is the absolute temperature of the surrounding. So this is about the Stephens-Boltzmann law. Now, as I said, the scientists given theory about the black body radiation. The German physicist Wilhelm Wein received Nobel Prize for the physics in 1911 for discovering this law. So what that law says, the lambda m into T is equal to constant. So lambda m, as I said, it is the temperature at which the radiation is maximum. So lambda m into that particular temperature. So this is a constant, and that constant is given by 0.002898 meter degree Kelvin. If it is in centimeter, it will be 0.2898 centimeter degree Kelvin, like that. So lambda peak, we can say lambda peak is equal to B upon T. As I said, lambda peak is the wavelength at which the energy radiation has a peak. So B is a constant. B is a constant of proportionality called Wien's displacement constant, and which is equal to 2.89 into 10 to the power minus meter degree Kelvin. Wein attempted to explain the black body radiation curves and derived formula, which is like this: E lambda d lambda is equal to C1 upon lambda to the power 5 into E to the power minus C2 upon lambda t into d lambda. So which is nothing but the energy emitted by the black body in the wavelength range lambda and lambda plus d lambda. So in that particular wavelength range, what is the amount of radiation emitted is given by this formula, where C1 is a constant which is given by 8 pi hc. H is a Planck's constant, we can say, and C2 is hc upon k, where k is the Boltzmann constant. So this law has certain drawbacks. As I said, the black body radiation curve, this law can be explained by the lower wavelength side of the black body radiation curve. If you apply this formula to the lower wavelength side of the black body radiation curve, it is applicable. But this formula, we cannot apply this formula to the higher wavelength region. So therefore, that drawback can be removed by the Rayleigh-Jeans law, which says E lambda d lambda is again equal to 8 pi kt of lambda to the power 4 into d lambda. Now this formula is applicable to the higher wavelength regions. So this formula is applicable to explain the higher wavelength region of the black body radiation. But again, its drawback is it cannot explain the lower wavelength region. So the Rayleigh-Jeans law explain the higher wavelength region of the body radiation, and the Wien's law explains the lower wavelength region of the black body radiation. Both laws are applicable, but at different part of the black body radiation curve. So the drawback of this Rayleigh-Jeans law is it cannot be applied to the lower wavelength region, and that drawback is called the ultraviolet catastrophe. Ultraviolet means it is a higher frequency region, or say we can say it is a lower wavelength region. So lower wavelength region cannot be explained by this law. That is called the ultraviolet catastrophe. In diagram we can show like this. So here this is the Rayleigh-Jeans law. So at higher wavelength side, sorry, at lower wavelength region, it is going towards this. So it cannot be explained by this Rayleigh-Jeans law. According to Rayleigh-Jeans law, the curve should go like this. That means this higher wavelength region can be explained with Rayleigh-Jeans law, and this lower wavelength region can be explained by Wien's law. But there is no one single formula to explain the nature of this black body radiation, and that is done by the quantum mechanics. That is invented by the Planck's law, that is Planck's radiation law. What Planck says, quantum law, the radiation is emitted in the form of quantas. So that is given by the Planck's law. So let us see the Planck's radiation formula, which is applicable to this entire region of this black body radiation. So Planck's quantum hypothesis in 1918, the Max Planck was awarded Nobel Prize for the discovery of quantized nature of energy. What is the discovery? Energy is emitted in the form of quantas, not in a continuous manner, but it is in quantas. So Max Planck given the theory, that is quantum theory, in 1900. What it says, E is equal to n into h nu. So one quantum is equal to h into nu. H is a Planck's constant, nu is the frequency, n can be 0, 1, 2, 3, and like that. So Max Planck developed a theory of black body radiation that leads to an equation for the intensity of the radiation. This equation is a complete agreement with the experimental observations. As I said, black body radiation can be completely explained by this quantum theory. He assumed the cavity of radiation came from the atomic oscillations in the cavity of walls. So let us discuss this part in detail in the next lecture, how he assumed the cavity radiation. That means the black body contains radiations, and that radiation is coming from the vibrations of atoms. As due to the temperature, atom starts vibrating, and that vibration gives out the radiation. Planck made two assumptions about the nature of oscillations in the cavity walls. That two types means two assumptions we can say to explain this type of oscillations. The energy is quantized, as I said earlier, and second is each discrete energy value corresponds to a different quantum. So every energy state is a different. So this type of assumptions we have already seen in the Bohr's theory. Bohr's theory also depends upon the quantum theory. So the oscillators emit or absorb energy when making a transition from one quantum state to another state. That we know the entire energy difference between the initial and final states in the transition is emitted or absorbed as a single quantum of radiation. So these laws we have already seen. An oscillator emits or absorbs energy only when it changes its quantum states. So in the yes, so that energy is equal to h into nu. So in the next lecture, we can explain or say we will derive this Planck's radiation formula by applying these conditions. And let us derive one single formula, and that formula, that is Planck's radiation formula. That formula, how it is applicable to the entire range of black body radiation. We can now derive the Wein's law from that Planck's radiation formula. We can also derive the Rayleigh-Jeans law from that single formula, that is Planck's radiation formula. So Planck's radiation formula is the universal formula that is applicable at all the ranges of wavelength for the black body radiation. So Wein's law can explain the lower wavelength side, Rayleigh-Jeans law can explain the higher wavelength side, but the Planck's radiation formula can explain the entire range of wavelength of the black body radiation. So in the next lecture, we'll see the this Planck's radiation formula derivation, and let us see how it is applicable, or say how the Wein's law can be derived from Planck's law, and also Rayleigh-Jeans law can be derived from the Planck's law. Okay, thank you so much. So let us meet in the next lecture. Thank you.